Welcome to Plutus. And today we are covering the relation between QC and KC. In this video, we'll learn about what is QC and what is its relation with the equilibrium constant QC. Apart from that, we'll see that how variation of one can lead to the change in the other, and using that we can predict where the equilibrium can shift based on change of concentration of the reactants and the product. So let's get started. First thing, we need to define what is QC. Now, in terms of formula, QC is represented in the exact same way as your equilibrium constant Kc is written. QC is usually written as concentration of product power raised to its stoichiometry divided by concentration of product, concentration of reactant power raised to its stoichiometry, while Kc is also represented in the exact same manner. So now, what are the two conditions that separates them? First thing, reaction quotient is called QC is called as your reaction quotient, and Kc is your equilibrium constant. Equilibrium. Now, here the word quotient represents something which is variable in nature, something which is variable and is continuously changing, while equilibrium talks about a static condition where the change in concentration of reactant becomes equal to the change in concentration of the product. Here, rate of forward reaction Kf, rate of backward reaction Kb. So that means reaction quotient or QC is carried or can be calculated at any given point of time. At any given point of time. While equilibrium constant is calculated at a very specific point when equilibrium for the reaction is achieved. So, for example, let's say I have a reaction in which two reactants A and B combining to give me a product C. It has some stoichiometry A, small b and C. Now let's say at any given point of time after 10 minutes, this reaction achieves equilibrium. Now, at this point, the concentration of A and concentration of B and concentration of C, at this particular point after the interval of 10 minutes, I can find the equilibrium constant using the concentration at this time. While before equilibrium was stabilized, let's say even at 9.9, let's say at 9 minutes 59 seconds. At this point, since equilibrium has not achieved, before this or at that time, whichever concentration I take, it will always give me reaction quotients. So now we have differentiated what is reaction quotient and what is equilibrium constant. Now let's try to learn the difference between these two. So let's say, assume this graph here. In the very first case, I am representing QC having a higher value Kc, while second case represents where QC equals to Kc, and this is the third case which represents where the Kc is greater than QC. Now, in this point, always remember that Kc is always of highest value. It is of highest value and it is the most stable state of the system. So that means no matter what happens is every system will try to achieve the value of Kc because it is much more stable and favorable by nature. So first thing, let me write first the separate formulas. Okay, we can use them later. So if you closely look at it, QC is represented by what? QC is represented by concentration of product and reactant. Now here, my QC is having higher value and Kc is having lower value. Now, since equilibrium is the most stable state, In which way it is possible that QC can reach up to a value of KC. So that means in this case I need to decrease the value of QC, and that can be done in two ways. First thing, I can either decrease the concentration of product, or I can increase the concentration of reactant. Let's say if concentration of product decreases, automatically the concentration of reactant will increase. So for this reaction, let's say which is in equilibrium in nature, the concentration of product can only fall when the product starts to decompose and starts to increase the concentration of the reactant. So that means if QC is having higher value than KC, then using this notion I can predict that my equilibrium will shift. Equilibrium will shift in backward direction. In backward direction. Now, the point where QC becomes equals to KC, that means the reaction is at equilibrium because there is no specified direction in which I want to move, since the concentration is equal and the system is already in its optimal state. Then the third case, you are having KC much greater than in value than your QC. Using the same notion, I have QC, concentration of products, divided by concentration of reactant, power is to their stoichiometry. So in this case, QC needs to increase its value so that it can reach to the optimal state. Now that can be achieved in which ways? When the denominator value falls off or the numerator value increases. These are the only two possible ways in which the value of QC can increase. So for the reaction that we have, A combines with B in equilibrium with reaction C, product C. So the concentration of product can only increase when A starts to form more products or the reactivity between A and B increases. And the concentration of reactant can only decrease when they try to react and give me more product. So that means in this case, whenever QC will have a lower value than KC, then by this value I can judge that this reaction will go into forward direction or I will get more amount of product in this reaction. So that's how you can use QC values and you can relate it with the equilibrium constant and predict the direction of the reaction, whether the equilibrium will move in forward direction or whether it will move in backward direction. So I hope this would have cleared your doubts regarding equilibrium constant Kc and the reaction quotient Qc and how they are related and how they can be used to predict the direction of a reaction by simply looking at their values. So if you found this video to be helpful, please like, share and comment, and in case of any other doubt, you can add it to the comment section and we'll get back to you. Or any other specific topic which you want us to make the video, you can also add it to the comment section. That's all for now. Thank you for joining.